Hi. Our topic for today is divisibility of integers. So our goal is to precisely present the definition of this notion and then see how to prove properties about divisibility from that definition. So we have two goals today. One is to improve our knowledge of divisibility, and the other one to improve our ability to write proofs. So let's first see a definition. You see the letters. Let n and d be integers, and d divided from 0. Then we'll say that d factors into n. So we can read it from left to right. D factors into n, or divides into n, and n is divisible by d, if and only if, by definition, there exists k z such that n equals k times d. So this is the definition. If we can prove the right side, then we can conclude that the right side is true. So let's see one theorem, theorem 2.41. For example, we want to prove the following theorem, the relation. We'll talk about relations in chapter 6, the relation of divisibility is transitive. Which means if A divides into B and B divides into C, then A divides into C. So how do we write that proof? Writing this proof is absolutely trivial. Just you need to assume, to make assumptions about statements that are on the left, and then somehow make a conclusion about the statements that are on the right. So assume that A divides B and also that B divides C. So that's our left side. And then if you remember that metaphor about crossing the river, we are on a verbal level, we want to go into a formal level, and that's exactly, this is kind of a verbal level, this is the formal level. So we'll translate both of them into formal level. So that means according to definition. So that means that the B equals K times A for some K Z. And C is equal L times B. We cannot assume the same witness, the same story as before, for some L in Z. Here it is. Now we transform those statements into two equations. Now we want somehow, in order to get the right side, to cross the river on the formal land. That means to get something about C in terms of A. Obviously, if you plug in B here, we'll get the following. C equals L times, and instead of this B, I will replace K. And then it's derivative law, it's LK times A, and then what? Then we are already here, we have equation. Now we want to go back to the verbal land. What would that be? So now we have that C equals, and LK is an integer. We can call it S or just say LK is an integer. We have a witness that A divided into C, which is our right side. So see, it was really extremely simple. We didn't need any special constructions or anything like that. Here's one important theorem that we'll call later. It is a little less obvious and a little less straightforward. There is a little assumption here that we have to build actually a real proof. Would actually need one of the techniques that we'll study later, and that is we'll need induction, but we'll just give something that sounds like a decent proof. So the resistance, so that n equals k times d. I like to have that on the board. So what? Every n integer n greater than 1 has a prime factor. So what would be proof with little objections? And you'll see something that we never finish, kind of intuitively. We can rely on it, but it's really not constructive proof. So we can say the following. Let n be arbitrary integer greater than 1. So there are two options. N is prime, or n is composite. If n is prime, we are done. Because n is its own factor, so n equals 1 times n is prime, so n divides into n, so as long as it's prime, that's its prime factor. But what if n is not prime? Then what happens? That means that n has non-trivial factorization k times l. Here's the crucial thing. Where none of the k and l, both k and l are greater than 1, and then what? So, and they are both k and l are less than n. Because if l is greater than 1, why is that? That's fairly easy. Because if l is greater than 1, then l is, let's say, greater than or equal to, so kl, n, which is kl, is greater than or equal to k, so obviously k itself is less than n. The same way l is less than n. So they are both less than n, so what happens? Then I'll continue focusing on smaller one of them, let's say k, and then I'll say the following. Now I do cases on k. K is either prime, and that's it, that's a prime factor of k, we stop here, or k is composite. And then if k is composite, we run the same. So left version is always stop if we have a prime, one of the factors. If that factor is composite, we go to the right and we keep branching. So here's the question, and that's the ambiguous part of this proof, and that is, how long can we keep branching? Can we keep branching forever, or we have to stop? We cannot branch forever because those k's that come on every step, that left factor is always smaller and smaller. So if we start from, let's say, 100, in 100 steps, we just don't have space anymore to go down, because then we'll reach 1. So at a certain moment, procedure has to stop. And when it stops, that means that we cannot split anymore. That means that actually we'll get a prime factor. So n is, or that factor, some k s is prime. And that's that prime factor. As I said, these dots make this not completely constructive proof, but anyway, in the future, we'll use this as a very important statement in our proofs, in our argumentation, and so on. All right. Then, based on this one, actually, we actually also gave another example, and that is, let me erase this. Example 2.4.2, prove or disprove. For integers, for if a divides into bc, then a divides into b, or a divides into c, for a, b, c integers. So the question is this statement true? I think that's how we formulate it there, yeah. So what? We can actually give not true. So I'll counterexample. Let's say the following: 4 divides into 2 by 2, because 4 divides into itself, but 4 does not divide into 2 itself, 4 does not divide into second 2 itself. So here's the counterexample. Left side is correct, the right side is not. So this is the statement that sometimes people use in their argumentation, but is incorrect. Just as a remark, the following version is true if A divides into BC and A and B have no common factors. We say A and B are relatively prime. And A and B are relatively prime. Then A divides into C. And we'll see a version of that theorem proved in a moment. All right? And now probably the biggest theorem of this section is prime factorization theorem. That is an important theorem because it's very often used in all kinds of proofs, not only in mathematics, in theory of numbers, but also in cryptography, and then coding actually very often relies on the importance of this theorem. So that would be theorem 2.4.3. That's how it is in the notes. Yes. Unique factorization theorem. So for any integer n greater than 1, there exists its unique prime factorization. Which means n could be written as p1 to alpha 1, p2 to the alpha 2, pk to the alpha k. Where what? P1, P2, Pk are primes. Did I write it that they go in? Yes, increasing order, that's easier. P1 less, so they are different primes. And I call them n, I better call them here as well. So it's the same in the notes. N1, N2, and K. N1 to Nk are positive integers. I will not write the proof of this theorem because it really would be even more technical and need more that technique of induction than what we had in the previous theorem. But it is important to be aware of this theorem and to understand it properly. So, so let me explain at least what this means. This is something actually that you studied in the basic algebra course. So if we have a number, let's say 120, then we can break it into product of primes. Why are we sure that we can always do it? Because we'll use the same technique as in the previous theorem. If it's prime, that's it. If it's not, we can break it. How? Whatever factor you see the most efficient is if you break it into both numbers of like middle size, let's say 10 and 12. And then what? If one of them is prime, we stop. If it's not, we keep going. So 10 is 2 times 5, and that's where we stop because they are primes. And then 12 is 3 times 4. And then what happens? 3 is a prime, so we stop. 4 is not, we keep going. We get 2 and 2, and generally what? Then we collect 2's because that's your P1, so in this case it would be 120 equals how many 2's? 3 of them. How many 3's? 1. How many 5's? It would be 1. So here is the prime factorization. Of course, these ends are 1's. So we have 3 primes as basis, and then exponents 3, 1, and 1. And this factorization is unique, so generally there is no other way to break this number into prime. So it's just quick comment. Why is that important? Because, for example, you can use it to code the sequence 311, like a little word. You can use it 120 to code the sequence 311. So 311 could be coded by 120. So 311 would be the message ABC CAA. So it's the word CAA, then you can code C as 3 as third in the alphabet, A with 1, A with 1, then you put 311 in the exponents, we multiply out, get 120. There are little improvements, but this is the main idea, how you can use huge numbers to code text. We'll talk about it in chapter 6. All right, so using this theorem, we can, for example, show the following. So, as I said, I'll not ask you to prove this theorem, but I will ask you in some problems to show me that you can use it. So, example says 10x equals 9y implies, and that's a question, is it true that 10x equals 9y implies that 10 divides y? Is this true or not? I would say yes. Why? Because we can say the following. We can write prime factor, because this is the same number, because it says equal. So that same number has factorization P1. We write it factorization P1 to N1, P2 to N2, Pk to Nk. And here's your 10x, but the same thing is equal to 9y. And then what? This 10 is actually 2 by 5. 2 times 5. So, since this is the same factorization, whether you multiply it this way or this way, 2 and 5 must appear somewhere there. So what then? So 2 and 5 are showing on the right side, so also they have to show up here, which is, this is 3 by 3. So 2 and 5, showing in that prime factorization, must show up here. But they cannot so 2 cannot show up here as 3, cannot show up as 3, so when we write prime factorization on the right side, that prime factorization must come from y. So we will say the following: 2 appears in the prime factorization of 9y. 2 does not divide 9, it doesn't appear there, of 9y, or we can say 3 squared times y. So 2 does not appear in the factorization 3 squared, so 2 appears in the factorization of y, so it divides y. The same thing for 5. 5 does not appear into 3 squared, so 5 appears in y. Here it is, 10 factored into y. Once again, when we learn Euclidean algorithm chapter 3, we can prove a little nicer version of this, but I hope that this also intuitively makes sense. All right. And now one more important theorem, the one that we'll call quite often, and that is theorem 244. It is quotient remainder theorem. Theorem 244. That's called quotient remainder theorem. What is this theorem doing? It's actually recording what we all know from elementary school, but something as a formal statement that we'll prove, and also we will then count on it and call it quite often when we write proofs. So I really recommend that you remember this theorem, understand it deeply, and kind of get comfortable using it, quoting it, and later on in our course and in different proofs. So what is this theorem all about? generally, before I even put the theorem on the board, let me play with a little example. And basically, what we do in example is never proof. I told you that many times. But examples sometimes illustrate and give us idea what to think about a proof. So let's say we want to divide 7 into 31. So generally, how can we do that? How can we write a program that will do that? And generally, what we say is the following. 7 is less than 31, obviously. So we are doing the following. 7 times 1 is 7. And 31 stays here. So we put 31 here. So then we try 1, and we say Q equals 1. I'm trying quotient to be 1. But did 7 reach 31? The answer is no. We are still below 31. Okay, keep trying. 7 times 2, or add an extra 7, so we get 14. Are we at 31? We are not, so we put Q equals 2. 7 times 3 is 21. We are not there, but anyway, we write Q equals 3. Of course, as soon as we refresh memory, actually Q equals 1 is crossed, Q equals 2 is crossed. So a new updated version of this. So we are kind of updating our quotient. We are trying, we see it's not time to claim that that's the quotient, and we keep going. And that's exactly how I can write the program. So 7 times 4 is 28. Are we still there? No, we are not. So we say Q equals 4. And then we keep going. 7 times 5 is 35. Whoops, we exceeded our number. In that moment, when we exceeded that number, we say stop. Don't improve, read your last quotient. So that's how we get that quotient, Q equals 4. And then what do? Then we know that from this 28, we didn't have a whole 7 jump until 31. So we can say the following: 31 equals 4 times 7, which is 28. And then there is a remainder. That one just how much is left, not enough to perform the whole step of 7, and that is 3. And those two numbers are, this is the quotient, and this is the remainder. Sorry, this is the divisor, here is the quotient, and here is the remainder. So quotient is 4, and the remainder is 7, divisor is 7 as well. All right. So basically, that's exactly what quotient remainder theorem says. And it says the labels are N and D. So given any integer n and positive integer d, there exist integers Q and D such that n equals, sorry, Q and R, D was given, Q and R, R and R on the right side, so that n equals QD plus R, but something else. If I were to leave it here, all these Q's would be good. But I want the one Q where R is not too big, where R is not enough to give me another D step. So that's why we say, but when we wanted this to call it remainder, R has to be greater than or equal to 0 and less than D. So not enough for the next jump. And that's called quotient remainder theorem. And theorem says, given an integer n and positive integer d, there exist integers q and r such that this is true. Moreover, they are unique. So what is the proof? Proof is basically the same one as what we had a minute ago. And that would be um, we'll just repeat the procedure that we did a minute ago. We'll go 1 times I'm doing it for n positive actually. If n is negative, you would need to adjust it a little bit, then I would start actually with negative. But let's do it for positive, and then next example you will see how it works for positives. So what then? Then we will look, at some point, we'll look at the following situation. D has to, there must be a point where QD will still below n or equal, but Q plus 1D will be bigger than n. So you are looking, what is the first time then with that Q plus 1D will exceed n. Then, and that has to happen because at least if you go to n, nd will be bigger than n. So when that happens, we say stop. And then we'll claim that that Q is the Q that we want. And then we just say let n minus qt be r. Because of this, here we'll have what? Since n is less than q plus 1d, then if we multiply, we get qd plus d, n minus qd is less than d, so r is less than d. On the other hand, n is greater than or equal qd, so obviously from here, so r is less than d, but from here, if I subtract, I get r equals n minus qd is greater than or equal to. And that's exactly what we want, that these two exist. And then you can just see in the notes, why are they unique? So just you assume that there are two, or actually it might be worth showing also uniqueness. But let me take a break here.